Hey guys, welcome back to another RASK Maths tutorial, and in this tutorial I'm going to be showing you guys how you can use the remainder theorem when either trying to solve for polynomials, for roots of polynomials, or just trying to evaluate polynomials. So basically what the remainder theorem says is if we have a polynomial f of x and we divide it by x minus a, so this is just well, it doesn't even have to be a factor, then what we're told is the remainder of this is going to be equal to f of a. So one place you might use this is when you're trying to find roots, and it's also known as factor theorem. Essentially, if you can find an a which gives you f of a equal to 0, then this a must be a root. So what you can do is you can basically just try and plug in f of a, try to find a root, so you're just basically guessing an a. If it's equal to 0, then you know x minus a is a factor, so therefore we found a root. So I'll show you an example of this. Let's say we had this polynomial x cubed minus 7x plus 6 is equal to 0. So let's make a guess that a equals 1 is a factor or root of this. Then we can check it's a factor, check it's a root by plugging in f of a, which is equal to f of 1, which is going to be 1 minus 7 plus 6, which is 0. Since there's no remainder when you divide x minus a by f of x, we can therefore know that x minus a, which equals x minus 1, is a factor of f of x. And from here, we can just divide by this factor, either using long division or synthetic division, to give us a reduced version of f of x, which only has the other roots excluding x equals 1, and then you can repeat this. So that's one way, and this is what people call the factor theorem. And yeah, that's essentially it. But one interesting thing that you can actually use is, well, you can use it to easily evaluate, or I should say quickly evaluate f of a. So clearly f of a is equal to the remainder of x minus a when f of x is divided by it. So what we can do is, let's say we wanted to find out what f of 4 was. Okay, now since this is just a cubic, it's pretty easy to do. We can just do 4 cubed minus 7 times 4 plus 6, which is going to be 64 minus 28 plus 6, or 42, I believe. Yep, that seems about right. So when it's a cubic, this isn't much of an advantage, but I'll show you the method anyway. What we can instead do is we can use synthetic division. So synthetic division is if we try and do f of x divided by x minus, well, I'll put x minus 4 in this case, then we essentially put a 4 over here as the root, put the coefficients of the polynomial, so it would be 1, 0, minus 7, 6, and then we can just evaluate this by doing this procedure. So we bring the first number down, 1, multiply by 4, put it over here, then we add these two to get 4, multiply that by 4 to get 16, add these two to get 9, and then multiply this by 4, and then finally we can just add these to get the final remainder. So what this shows is these are the coefficients of, I'm just going to call it result. I can't remember if it's called quotient or something else, but I'm just going to call it result polynomial. and then this is the remainder, which we know is equal to f of a. So what we've basically done is just by a few addition and multiplications, we're able to calculate the remainder. And notice how we didn't have to raise anything to powers or anything. So this could be a useful way of quickly evaluating a large polynomial. For example, let's say we had f of x equals x to the 7 plus x to the 6 plus x to the 5 plus x to the 4, and we'll just carry this on. So clearly, I'll just add a plus 1. Clearly, if someone asked you to evaluate what f of 5 was, this would be pretty big. You'd have to work out each of these individual powers. But now, instead, we can work it out by just simply putting it in. So we put a 5 over here, and then we just put in the coefficients. So 1, x to 7, x to 6, x to 5, x to 4, x to 3, x to 2, x to 1, x to 0. So these are all the coefficients. And then what we can do is quickly evaluate this by using the same method. So we're going to end up with 1, 5 there, 6, 30, 31 there, 155 here, 156. And yeah, this just continues. So it's still a pretty tedious process because I suppose you still have to add up, like you still are going to end up with a pretty large number. I think the next one will be 780, and then you'd continue until you got your remainder over here. Sorry, your remainder would be over here. And yeah, but it's faster than finding out what f of, or 5 to the 7 is, and all of that. I mean, 5 to 7 isn't too bad, but if you had a different number, it might be a lot worse. So this is just a fast way of evaluating f of a. So yeah, those were the uses of the remainder theorem. Hopefully that was useful. Thanks for watching, and I'll see you guys in a future tutorial. Bye.